Section 1.4, Building Functions from Functions. So in this section, the objectives that we're going to look at are basic function operations, including composition. So we're going to add, subtract, multiply, and divide functions, as well as plug functions into other functions. We're going to evaluate piecewise defined functions. That's a function that behaves differently based on what x values you're plugging in. And we're going to apply and evaluate something called the difference quotient. Now, the difference quotient is kind of just a little bit of extra fun for pre-calculus, but it is the foundation of calculus. So we're going to play with the algebraic portion of the difference quotient in this course, and then at the beginning of calculus, that difference quotient is going to come back, and it's going to serve as a foundation of everything to come after. So starting with our basic function operations. So as I said, operations such as addition, subtraction, multiplication, and division can be applied to any type of function. What we're going to start by looking at is just the notation though. If I say something like this, f plus g, that's the same thing as saying f of x plus g of x. So it's just kind of an extra lazy way to write function notation, or the sum of functions. You don't even have to write the x. You could just write f plus g and understand that it means f of x plus g of x. This does not say f plus g times x. This says f of x plus g of x. We're not multiplying times x. X is the input value. I can do the same thing with subtraction, multiplication, and division. So again, just two different ways of writing the exact same notation. If I see f plus g, f minus g, fg, or f over g, that just really means f of x plus g of x, f of x minus g of x, f of x times g of x, f of x divided by g of x. And then there's the last one, the fog function. So hopefully you remember from Algebra 2 this little notation right here. This is not a multiplication, this is an open dot, and it means composition. So it means to take the second function g and plug it into the first function f. So f of g of x. So if I knew what the x value is, for instance, if the x value was 2, I would evaluate g of 2 first, get an output, and then that output acts as the input for the f function. Again, this is called the composition function. So let's look at some examples. Here are two functions. F of x equals 2x minus 5, g of x equals 2x squared. I want to perform each operation. Why don't you give each one a try and then hit play when you're ready. So looking at the first one, f plus g of 2. Again, this does not mean add f and g together and multiply it times 2. It means plug into f and g and add them together. So this literally says f of 2 plus g of 2, so I'll just evaluate each one separately and add them together. So if I evaluate f of 2, 2 times 2 is 4, 4 minus 5 is negative 1. Then I'll evaluate g of 2. 2 times 2 squared is going to be 8. Add them together, I get 7. So f plus g of 2 is 7. Now let's do it again. This time I want g minus f, and notice I'm not plugging any x value in. I'm just going to leave it in terms of x. It still says g of x minus f of x, so I'm just going to subtract the two functions. And this is a situation where it seems easy enough, just subtract, yet this is probably one of the more common questions to get wrong on the Chapter 1 test, because students don't pay close enough attention because it seems like such an easy question. So let's see what happens. G of x is 2x squared. F of x is 2x minus 5. I'm going to subtract, and I might say, okay, I'm done. I can't really combine any like terms, so that means I can't do anything else. This is my answer. But that's where we make our mistake. We are not subtracting just the first term. We are subtracting the entire function f of x. When you are subtracting something, you have to pay extra close attention. Specifically, I suggest put it in parentheses. We are not just subtracting the 2x, we are subtracting 2x minus 5. So I have to distribute that subtraction sign to get negative 2x plus 5. Again, when you are subtracting, remember that when you plug something in, you're using parentheses. So subtracting across parentheses, you have to distribute that subtraction. So here is my final answer, since I can't do anything else. Next one was f times g. So f of x times g of x, we can just distribute the 2x squared. I get 4x cubed minus 10x squared. Can't do anything else. Final answer. And then f over g, in other words, f of 4 or negative 4 over g of negative 4. So I'm just going to evaluate f of negative 4, evaluate g of negative 4, attempt to divide. and call it a day. So f of -4 would be -13. G of -4 would be 32. I'm going to attempt to divide, but 13 and 32 is not going to divide pretty, so I'm just going to leave it as -13 over 32. Now we've tried the easy ones, let's look at the composition, and hopefully you'll discover that these are the easy ones as well. So why don't you see what you can remember, give each one a try, hit play when you're ready. Alright, let's look at the first one, f of g of x. Remember that fog function just means we're going to take the g, the second function, and plug it into the first function. So again, f of g of x. So g of x is your input value. This is like saying if I asked f of 3, 3 is your input value, I would plug 3 into x for the function f. In this case, I'm going to plug in the entire function g of x into the function f. Remember, you can always think of function notation as a fill in the blank. Where the x is just a placeholder. So in this case, instead of writing 2x minus 5, I'm going to plug in the entire function g of x. So g of x is 2x squared, so instead of plugging in x, I plug in 2x squared. Anywhere I see x, I replace it with the entire function g of x, or 2x squared. And then from here, I'm just going to simplify. 2 times 2 is 4, so I get 4x squared minus 5. I can't do anything else, so that's my answer. Let's do the same thing, but reverse it. Instead of plugging in g into f, this time it's f into g. So again, g of x represents a placeholder. X is going to be plugged in, is going to be replaced by f of x, which is the entire function 2x minus 5. So I'm going to plug in 2x minus 5 anywhere there was an x before and clean it up. Now this time I can multiply through the 2x minus 5 squared. Following order of operations, I got to square it before I multiply it times 2. And when I'm squaring something, that means multiply it times itself. So I can think of this as 2x minus 5 times 2x minus 5. When I FOIL it out, I should end up with 4x squared minus 20x plus 25. Distribute the 2, 8x squared minus 40x plus 50. Final answer. And then let's look at this one. This time I'm going to take f and plug it into itself. But before I do that, I actually have an input value. I'm going to start with the 1. So this literally says f of 1. So I'm going to evaluate the inside first, f of 1. 2x minus 5 becomes 2 times 1 minus 5. So that's 2 minus 5 is -3. So the inside is f of 1 is -3. And then f of -3, I get -11. All right, let's look at piecewise defined functions. This is an example of what a piecewise defined function looks like algebraically. As I said, a piecewise defined function is a function that behaves differently based on the x values, based on the input values. So here is a situation where the function behaves 3 different ways. When x is less than -5, it's the quadratic x squared. When x is between -5 and 4, it behaves like the line 2x minus 1. But when x is greater than 4, it behaves like the square root function square root of x. So depending on what x value I want to evaluate, I will apply it to the appropriate portion of the piecewise function. So starting with f of 7, in this case the input value x equals 7. So I'll look at each of the domain intervals. X equals 7 fits into this last interval because 7 is greater than or equal to 4. So in order to evaluate f of 7, I will use the square root of x. So plug in 7, I get square root of 7, just like that. Wanted to try the other 3, hit play when you're ready. So the second one, f of -3, I'm going to look to see which interval -3 fits on. Well, -3 is going to be between -5 and 4. So I'm going to use 2x minus 1 to evaluate f of -3. And when I do that, I get -7. The third one, f of -10. -10 is going to fit on this top interval. -10 is definitely less than -5. Plug it into x squared, I get 100. And then the last one, f of 4. Now notice 4 appears twice, but 4 actually only belongs to this interval right here, x is greater than or equal to 4. So to evaluate f of 4, I'm going to use the square root function, so I get 2. All right, on to the difference quotient. Now, the difference quotient, again, as I said earlier, is the foundation of calculus. So what we're going to do here is we're going to play with it a little bit in terms of the algebraic portion of the difference quotient. We're going to learn to evaluate a difference quotient. But when we get to calculus, that first couple of chapters in calculus, the difference quotient quotient is going to come back, and you're going to see how everything in calculus builds on what is established by the difference quotient. And the difference quotient really is just a fancy way of describing slope. So let's start with a curve. Here's a curve right here. Now, again, in terms of Algebra 1 and Algebra 2, the idea of slope only applies to lines. But once we get to calculus, we realize that slope can occur anywhere. It can occur for any type of function. So I can describe the slope of even a curve like this. The difference is that the slope is constantly changing. So at any given point in time, so like right here, what I can do is imagine a line tangent to the curve at that point. That line has a slope. And then this point right here, I have a different slope. And then this point right here, I have a different slope. Every time I draw a point, I could draw a tangent line to that point, and I can get a slope of that tangent line at that point. So at any given point in time, the slope could be something different. And notice, as the curve increases, the slope of each line gets steeper and steeper and steeper. So as the slope is increasing, the tangent line slope is increasing as well. Now, for our purposes today, we're not going to look for the slope of those tangent lines. That's what calculus is going to be all about. We're going to imagine the slope over a larger interval. In other words, if I pick 2 points on the curve, what would the average slope between those 2 points be? Now, let's start by identifying what those 2 points are. Keep in mind each point is an x and a y value. So let's call this one x1, y1. This one would be x2, y2. So what we're going to look at here is the average slope between these 2 points, which would be represented by this secant line. Remember, from geometry, a secant line is a line that intersects a curve 2 times. A tangent line is a line that intersects once. A secant line is something that intersects twice. So the slope of that secant line could be thought of as an approximate slope of the curve between those 2 points. So slope of a line is just y2 minus y1 over x2 minus x1, so we can use this slope of this secant line to approximate the slope of the curve. Now, what I'm going to do next is I'm going to redefine some variables, because of course as we move ahead in mathematics, we like to make things a little bit more complex in order to keep the wimps and weenies out. We like things to look complex when in fact they are actually quite simple. We don't want to let everyone into our mathematical club. We want to be seen like we are special, so we're going to take an easy idea and make it a little bit more complex. And the way we're going to do that is, instead of saying x1 and x2, I'm going to define the distance between the x values just to be h. H represents the distance between the x values. So if I call x1 x, that means x2 is really just x plus h. So instead of writing x2, I'm going to write x plus h. And with that, instead of calling this y1, remember y is really just a placeholder for f of x. If I plug in x, the y value would just be f of x. If I plug in x plus h, the y value would be f of x plus h. So instead of using the old notation of x1, y1, x2, y2, we can say x f of x, x plus h, f of x plus h. So then we can use these values in the slope formula and start replacing things. Instead of saying x2 minus x1, I can say x plus h minus x. And notice what happens. X minus x is just h, which makes perfect sense because I defined h to be the distance between these two x values. x2 minus x1 represents the distance between those two x values. So it simplifies just down to the single letter h. And on the top, if I do my substitution, instead of saying y2 minus y1, I could say f of x plus h minus f of x. So this right here, this formula right here, again, is still just the slope formula. It's just written using a slightly different notation. But we now like to call it the difference quotient. It's a difference because I have subtraction. It's a quotient because it's a fraction. So the difference quotient, again, is just a fancier way of writing the slope formula. Now notice I've got this h cannot equal 0 because of course the denominator can't be 0, and I'm just going to state my domain off to the side. We really don't do a lot with that. It's just kind of part of the package. Obviously h can't be 0. It's important to state that off to the side. A lot of times I forget it. Not a big deal. It's there. We know that h can't be 0. It kind of is implied. So let's look at an example. Let f of x equal x squared minus 2x. Evaluate the difference quotient, f of x plus h minus f of x all over h. In other words, I want to come up with a formula that would represent the slope of the curve x squared minus 2x. When I'm evaluating a difference quotient, I'm coming up essentially with a slope formula, in this case for a curve. So what I'm always going to do is I'm going to start with the hardest part of the problem, this f of x plus h. I'm going to figure out what f of x plus h is before I do anything else. So again, this is just like function composition that we did earlier. I'm going to take, instead of writing f of x, I'm going to replace all the x's with the summation x plus h. So x squared becomes x plus h squared, minus 2x becomes minus 2x plus h. So anywhere I saw an x, I replaced it with x plus h. So let's clean it up from here. X plus h squared. Again, you can FOIL that out. It's going to become x plus h times x plus h, or x squared plus 2xh plus h squared. And of course, I could also distribute the negative 2 and get negative 2x minus 2h. So remember, this is not my answer. This only represents this small piece of the puzzle right here. All right. So now let's put the rest of it together. I've got my f of x plus h. It's going to be part of a fraction. That f of x plus h goes on the top left, and then I'm going to subtract f of x, the original f of x, x squared minus 2x. And just like before when we were subtracting functions, you got to make sure that second function is in parentheses. X squared minus 2x is in parentheses because, again, I am subtracting it, and I have to distribute that subtraction. So let's go ahead and do that. Minus x squared plus 2x. Now from here, it's just a little bit of simplification. I'm going to look for terms that are going to cancel. And look at that, the x squared and the negative x squared, those are going to cancel. I've got negative 2x and positive 2x, those are going to cancel. And I'm left with terms that all have an h in them. Now, a hint for the future, this will always happen. Notice that all of the terms in f of x canceled out. This will always happen. If that doesn't happen, you did it wrong. Start over. The terms of f of x should always cancel out. You should always be left with a bunch of terms that all have an h in them. If you have terms that don't have an h in them, you did it wrong. Start over. F of x will always cancel out, and you'll always be left with terms with an h in them. So because all the terms have an h in them, we can actually factor out an h. So 2xh becomes 2x, h squared becomes h, 2h becomes 2, the h goes to the outside, and notice I have an h on the top, I have an h on the bottom. We can cancel out that h, and we're left with 2x plus h minus 2. So that formula right there represents the slope of the curve, x squared minus 2x, at any given x value, 2x plus h minus 2. Now, as you go on to calculus, you're going to go a little bit further than this. You're going to take a couple more steps, but for now, that's where we're going to stop. So let's look at another one. Why don't you try this one on your own? Hit play when you're ready. All right, we're going to follow the same process as we did on the last one. Start with f of x plus h. Replace all the x's with x plus h, and simplify. This can be distributed. This can be FOILed out. Don't forget to distribute the negative. We're going to end up with 5x plus 5h minus x squared minus 2xh minus h squared. This is my f of x plus h. Let's put it into the fraction. It goes on the top left. Then we subtract the original function, 5x minus x squared. Once again, we will distribute the negative and get this guy. We can start cleaning it up. Remember that the terms of f of x should always cancel. In this case, they do, so we know we did it correctly. Also, all the terms left over all have an h in them. We know this is supposed to happen because they're supposed to cancel with the h on the bottom. Just like before, I can factor out the h, cancel the h. I'm left with 5 minus 2x minus h. Final answer. All right, let's do one more. This time, though, instead of evaluating f of x plus h minus f of x, let's do f of 3 plus h minus f of 3. So this time, what the question represents is not the slope at any given x value. This one represents the slope specifically at x equals 3. So in other words, this is like finding the slope of the tangent line. So let's see what happens when I, instead of using the x as a generic x value, we use 3 as our input value. Now the process is going to stay exactly the same, except when we're done, we're not going to have any x values. They're all going to be evaluated at x equals 3. So let's start it off the exact same way we always do. So instead of replacing with x plus h, we're replacing with 3 plus h. So x becomes 3 plus h, so we have 2 times 3 plus h squared plus 5. FOIL out the 3 plus h. We get 9 plus 6h plus h squared. Distribute the 2 and add 5. We have 23 plus 12h plus 2h squared. So put it into our difference quotient. That goes on the top left. Then we are going to subtract f of 3. This time we can actually evaluate f of 3 to start with. Instead of just leaving it as 2x squared plus 5, it's 2 times 3 squared plus 5, which of course is 23. Clean it up from here. Notice that 23, just like we always expect to happen, this value always has to cancel. So 23 and 23 are going to cancel. We're left with 12h plus 2h squared, just like it always is. All the terms have an h in them. We can factor out the h and cancel. We're left with 12 plus 2h. So 12 plus 2h represents the slope at x equals 3.